Yeah, hello and also welcome from my side to today's webinar powered by Digi-Key with the topic aluminum electrolytic versus aluminum polymer capacitors and how are the respective advantages used correctly, or how we also say it, how the benefits are used correctly. Yeah, my name is Frank Bohane, and as Amelia already said, I'm the lead of the technical engineering for ICAP Iris. And we are focusing on design in support, bringing in our components into design, and also do measurement requests and help the customer to find yeah, the right solution for his application. Yeah, so today agenda would be as follows. So we will talk about the construction of the aluminum capacitors itself, so polymer and aluminum. We have a look at the equivalent circuit. We talk about self-healing capabilities of those two product ranges. Also about the expected life calculation, so how you can calculate it and how it will look. And then the end, of course, how the benefits are used and what kind of advantages it brings to the application. So yeah, please grab your coffee, relax and have a good time with our content of today. So first we will talk about the construction of aluminum capacitors. This includes THT and SMD, and it doesn't matter if it's aluminum electrolytic or aluminum polymer capacitor. Construction of the parts is quite the same, with one special step who makes the difference. Looking at an overview, so the differentiation about the electric capacitors. So there's some differentiation between the used electrode material here on the left side, and then also about the properties of the electrolyte. So we can use our aluminum as we do for our caps at the moment, but of course there are manufacturers on the market. They provide also tantalum or a niob capacitor. And then there's a distinguish between wet and solid. So wet would be the classical electrolytic capacitor, and solid would be the electrolytic polymer capacitor. When we are using the aluminiums, we use for the dielectric material, we use the aluminum oxide. It has a permittivity with around 9.3. So permittivity is the gain of the how we can boost the capacitance. And looking at tantal and niob, it would be getting better. So with tantalum and niob, you will get a better volume efficiency of the capacitance, but tantal and niob have also some special handling, so you have to know how to use them. But of course, they are also available on the market. But today, we talk about the aluminum capacitor. The construction, yeah, you can easily build your own capacitor in the kitchen. So you have to use some aluminum foil and a separator paper. You have to wind it and make contact on each foil or film. Then you get an capacitance. So yeah, because the aluminum capacitor is has a polarization, we have a dedicated anode foil and then also a cathode foil, and then a separator paper between. So this separator paper is soaked with electrolyte. So we dip it into an electrolyte, and then the separator can soak up the electrolyte and then use as an material also who helps to build a oxide layer. What is really special, you see in the right picture here, that the oxide layer here, this big bold line here, this is the actual dielectric material, and also we use then the electrolyte and also the foil to contact these electrolyte to the outer world. So not really the cathode foil is the minus. It's more or less the electrolyte and the oxide layer. So this is quite special. But of course we have the two pins and to connect it to the PCB. Then it's get a little bit more specific or more precise for the aluminum electrolytic capacitor. So on the left corner here, you see how its winding of the foil looks like. With it's wet, so we destroy the cap to make this picture to see how it looks inside. On the left corner here, lower corner, you see how what kind of components are placed to build up an electrolytic capacitor. So you have of course, your aluminum case, then you have your element with the pins already there with electrolyte, and then you have your sealing, so your rubber, to make it in a complete system, everything sealed. Looking more precise on the winding. So you have your base film here, your anode foil, which is roughened. So the anode foil gets a special treatment, and then your cathode foil, just a normal foil. You have your lead wire here. And one important production step is also about the stitching. So the stitching means how the pins will be connected to the foils. And this process is really important because it also defines about what is the ESR and what is the losses. Because when a good connection is there, you know the losses, the ESR, so the ohmic losses will be lower. And here in this picture, you see a microscopic view of the stitching, how it can or how it looks. So it's really that it's getting stitched to the foil. Compare this to the polymer capacitor. So polymer capacitor also have the aluminum case, also the winding here inside with a separator paper and a rubber, and also the pins get stitched to the foil. Here is some special that the pre-treatment of the anode foil makes them black because of the polymerization. So it has a special color. Also the cathode foil here, but you see the difference between cathode foil and anode foil. Also here the pins get stitched, so you see here also the stitching. Maybe you can let me go once back. You see also here a different amount of stitching. So here's 6 stitches. Here's 4 stitches. So this means you can change the parasitic parameter or the equivalent parameter also by your production steps. When everything round up, it looks like this here. So this is a winding of a polymer capacitor, and also here a picture of the foil again. Yeah, one thing about the roughness of the foil. So depending if you have a low rated voltage or a high rated voltage, the roughness is different. So low rated voltage has less roughness. The treatment is done by electrolysis, and depending what kind of roughness you made, it's really have then the voltage strength and also mechanical strength, and it could look like this in the right corner here or like this. This is what we have to define in production when we define a certain capacitor. For the polymer, we have also here an impregnated anode foil. It's the same winding process about the traditional electrolytic capacitor. We are using an monomer, and then with an heating process, the monomers getting polymerized to have a polymer chain, and this is a special treatment, special heat treatment, exothermic reaction. So the drying and aging process of this takes up to 8 hours, and the temperature is around 120 degrees. So it's an temperature process to bring this monomer to polymer to get then the advantages of this now solid capacitor. But we will go there in a few minutes. First, I would like to talk about the equivalent circuit of a capacitor. Also, it's the same with THT, SMD, and so on. The values change, but the basic is still the same. So it's the same physics behind. So the ESR, causes heating, so it causes losses. ESR defines the dielectric and the ohmic losses, and this will generate heat. Also with the ESR, when there's a ripple, or there's a voltage applied and ripple current and so on, it will be heating up the component to itself heating, and we have to check the maximum temperature, operating temperature. Normally the ESR is specified with 120 Hertz or 100 kilohertz, 20 degree. We measure over the complete frequency range and put this data to our expert tool. There you can find a complete overview about the whole frequency range, but also we measure at 20 degrees, so laboratory temperature. And you can calculate the ESR out of the tangent delta, so the dissipation factor, and vice versa. Also, you can calculate your impedance or your resistance out of the capacitance when you know the frequency. But we also measure the ESR over the complete frequency range, so you can have a look in our real expert tool. Yeah, when we are applying ripple current as a kind of AC from our switch on power supply or something, the ripple current causes heat inside the capacitor due to the ohmic resistance and the dielectric losses. And it's caused by the changing field strength in the current which flows through a capacitor. And we can achieve a low ESR when we're changing the electrolytic. So mostly the conductivity of the electrolytic material is important, but we also have to check what electrolyte we use because of temperature, behavior, lifetime, and so this is also a trade-off what we have to figure out. But compared electrolytic to polymer, there's you see in the right corner here 4 Siemens per centimeter compared to the 0.04 Siemens per centimeter. So the conductivity of polymer is 100 times higher than for electrolytic. Therefore, we can achieve also the low ESR here. Yeah, having a concrete overview about aluminum electrolytic, 10 microfarad, 25 volt, and also 10 microfarad, 25 volt for polymer. When we check the ripple current rating with 100 kilohertz, you see we have 90 amp compared to 2.2 amps at the same frequency. You can also have a look in our online tool with expert to see the ripple current graphs with temperature and frequency. This is a hint to check the current capability to select the best solution to your specification of the application. So the impedance itself, so also the inductor have its impedance, so it's the resistance for the alternating current. It could be calculated out of the ohmic losses and the inductive and the capacitance, the parasitic capacitance. And when we have your impedance curve here, you see this slope is from the capacitor, so the capacitive part. The green is not a line vertical, it's more or less this point here. So the minimum point is defined by the ESR, so the purely ohmic resistance, and then it goes up because of the ESL of the component. So depends what kind of component you are using. The curve looks different, but this is from an MLCC, so it's quite a sharp definition here. Also, when you're looking at the ESR, so this is a real curve of the ESR. we can measure here at 3 megahertz or 1 megahertz. It's quite the same. The minimum ohmic resistance. And this is what I talked before, that we have all the data available, and you can have a look inside our online tool. Also, of course, because we have different sizes, there's also an impact of this form factor, especially for the ESL. You can imagine when we make the parts longer, so also some kind of thinner, we have more activated surfaces, so we have more surface area to make with less winding the same capacitance value or more capacitance value. So when we decrease the number of windings, and therefore we decrease also the ESL of when we have to increase the winding, because we have the surface is not the square of the surface is not big enough. We have to make more windings. Also the ESL goes high. So it's the same with the inductive parts. Depending on the core shape, you need more or less windings. So we have a difference in the diameter and length relation. And also when the ESL is really important, what you can do, you can make a parallel connection of capacitor. Of course, then you reduce the ESL. Also, one hint, when you have when you have not so much space to use the THT types, you can also bend them in your application with 90 degrees. Then the leakage current itself, or the leakage current defined by the isolation resistance. Here we show our SMD type, 220 microfarad, 6.3 volt, 2000 hours, 105 degree. So when you see the values in the data sheet, it's measured after 2 minutes, and then this definition comes to the data sheet. It's not done because it's the best, it's done because it's fast. You have to imagine when we measure it until 20 minutes or even 30 minutes or higher, then the qualification and the component measurement would take too much time. It will also increase the cost, but we did it. So after 6 minutes, it's also quite longer. We have compared to the after 2 minutes, we have here 1100 nanoamps. Compared to 6 minutes, it's only 688 nanoamp. And now we invest more time. So this is what you see here. This is also some measurement accuracy problem. It will not rise again. It's like an asymptotic behavior. So we reach around 400 nanoamps after a long time leakage current measurement. So we can do the measurement, and we can do the measurements for you, but we have also the definition data sheet with the 2 minutes. So, but please keep in mind that the leakage current will always go down by time when you use it in the application. Then coming to the self-healing capabilities of the different technologies, because they act in a different way. So aluminum electrolytic capacitors, they have self-healing capabilities. Self-healing means, imagine the oxide layer is the separation between plus and minus, more or less. And when the oxide layer is damaged, then leakage current will increase, and in the worst case scenario, there will be a short. So this is why the oxide layer is really important. And with this self-healing capability, the part can recover the thickness of the dielectric layer, and therefore this is really a good behavior. And also the thickness is important of the performance, because the complete voltage across the capacitor will be handled by the oxide layer. And the thickness of the oxide layer will be reduced by time. Because when the time makes everything worse, more or less, so there will be chemical reaction, oxidation, and this will reduce the dielectric layer. when the capacitor is not in operation. Also, overvoltage and wrong polarity damage the oxide layer and should be avoided. And also thickness will be increased in operation or when we do some forming. Forming means we apply the voltage to current limit. So we control the current and then the oxide layer will be built up again. So when we do a comparison between aluminum electrolytic and aluminum solid polymer, we have in the electrolytic one, we have water, so liquid. The oxygen ions will react with aluminum and create a aluminum oxide layer again. So it's the self-healing capability, but this will reduce over time because yeah, when the water is consumed to make self-healing, or when there's a high temperature, then there will be some diffundation of the liquid. So the capability of the self-healing will be getting less and less over time. For the solid polymer, it's in solid inside, so there's really limited water inside, and so it's a very limited self-healing possibility. But of course, when there is no wrong polarity or no overvoltage, it's a really reliable product over long time. That is a good hint to go to the next topic. It's the expected lifetime calculation for the polymer and the electrolytic one. Yeah, when we are looking at the formula to calculate the expected life, there's a huge difference for the two technologies. For aluminum electrolytic, there's the traditional Arrhenius equation. So when you go down 10 degrees in temperature, you double your lifetime. And compared to polymer, when you go down 20 degrees in temperature, your lifetime get multiplied by 10. And from the formula here, expected lifetime, here's a specific lifetime, and then T0 and Tx is the operating temperature, and 1 is the ambient temperature. That's really different in the way how the lifetime gets calculated. Yeah, when we use the formula and play a little bit, we created this table to show you the difference between the technologies in lifetime. So we assume 2000 hour aluminum electrolytic and polymer cap, and then we go down to 65 degrees. Why? Because we think this is a really common temperature inside an application. Of course, you have also 85 and higher temperatures when you're thinking about you have a device laying in your car or something in the summer. But for industry customers, should be in an affordable temperature. And with the aluminum polymer cap, we have our 200,000 hours expected lifetime at 65 degree compared to the aluminum electrolytic with the same initial endurance, only 32,000 hours of lifetime. So this is in factor around 5 times higher than with the electrolytic you have with the polymer capacitor. And also one possibility is, of course, you can increase the initial endurance here. We can increase it for alu caps with 5,000 hours. And then we have 8,000 hours at 65 degree. So it's just 2.5 factor. But of course, we still have our 200,000 hours. And it's also possible on the market to have polymer caps with 125 degree rating. So imagine you go from 125 degree down to 65 degree. So you have around 10 million 20 million of lifetime, or 2 million of lifetime, sorry. So this is really high. But there's of course some limitation with this lifetime. So this is a graph also for your reference, to showing the different expected lifetime in hour when you have different endurance settings. But most of the manufacturers only expect lifetime calculations between 10 and 15 years, because I would say no manufacturers measure the real lifetime in 15 years. This is all accelerated lifetime and mathematical equations. This is why the maximum I know is 15 years, where the manufacturer can make some assumption. So also this is same for our parts. Yeah, the conclusion, so between the two technologies, to make a short overview, I would say. So when you have a filter, so both technologies are good for, depends what kind of filter you want to build up, depending also of the damping of the filter and so on. So there's everything good here. Also for DC-DC converter, you can use both technologies. You will see also later what is the difference between battery powered application. Please keep in mind that you have a higher leakage current with the polymer. So for battery application, it's not so recommended, because over time maybe the battery get sucked out by the polymer. So this also with this low or green energy, you have with both parts your leakage currents, and but for polymer more than for aluminum electrolytic. Also regarding low temperature, there is a really big advantage for the polymer, because it's solid. It cannot freeze. So when you have operations in really worst case conditions in the Rocky Mountains or somewhere else, with really low temperature, then the aluminum electrolytic can get freezed and then change the complete electrical behavior or specification. So here polymer is a really good alternative. For audio application, this is really based on what you want to build up. If there's a special need, you can also use both. Also for the higher vibration, we would recommend to use the aluminum electrolytic ones, because the polymer have a solid inside. The solid cannot really handle the vibration so well, and so when you have a liquid inside, the liquid can handle the vibration little bit better, and so we would recommend the aluminum electrolytic ones. To show you the benefits, or what this all means, what I talked in the last more or less half an hour ago. We build up an power supply, and small power supply, and check the behavior of the power supply with the different technologies. So we use a buck regulator. So it's just of course, Billam's power supply is always challenging, but this is just a really small one, simple one. I used an analog chip. I go from 12 volt to 5 volt with 1 amp and ohmic load, so no inductive or capacitive load. Switching frequency is 1 megahertz, and it's monolithic synchronous converter. And I use an LHMI molded power inductor. And what you see here also is the input filter. Here's input inductors, input capacitors. Here's the output or the inductor, and the output capacitors here. Here's the schematic, here's the layout. I know that there could be done improvements for the layout. I also did it, so I have also a second version of it. So when you find some really failure, or you think the layout is not as good as it should, I can agree. But one good thing was that this switch mode power supply makes noise, and this is what I want to show and also measure. So I do a conducted emission measurement. in a lab, so in our lab, in our headquarter, with an Rohde & Schwarz test receiver. I have a 2-line V-network listen, and I measure it everything in the shielded room. And I have my dude here with a load. I hit the cables and measure then the conducted emission. I also measure the radiated emission, but this is not a topic here. So radiated emission was really critical, and I failed. I cannot do anything to pass. I failed because the layout was so bad. But in the second version, I also do a better layout and I passed it. But here I will talk about the conducted emission. So I have now no input filter. So no no input filter what you see in the beginning, just the input capacitor, the bulk and the MLCC. For input capacitor, I use an aluminum electrolytic one, 47 microfarad, 16 volt with an ESR around 411 milliohm, ESL 19 nanohenry. You can have a look at Red Expert to see the curves, and this is why I get 411, because I can really precise move the cursor. And what you see here is that around 1 megahertz, so this is my switching frequency, and then the fundamental frequency, there's the biggest peak, and it goes up around 100 dB microvolt. So this is way too much about the TISPA 32 limits, quasi-peak and average. And also the second one and the harmonic one are way too big that I pass the conducted emission test. So yeah, why this is so, or where does it comes from? So we have the symmetrical voltage at the input, and yeah, you have your input capacitor here. So because it's parasitic, you have your ESR, ESL. You have also here your supply lines. They have an ESL and also an resistive part, and because of this, and because the ESR and ESL is high, you get an resonances. So possible resonances could be by the supply lines, the L, so the resonance with the ESL and the capacitance from the input capacitor. And this is what you see here is the mathematical equation why we get the drop. And the voltage drop, what we can calculate also is this what we measure with the EMI receiver. And of course, when the ripple is really high, we measure this 100 dB microvolt. Yeah, what I did, I changed technology. So I changed to an polymer and an MLCC, also 47 microfarad, 16 volt. ESR is now 20.7. ESL is also lower. You can check it with an Red Expert also. And then I decrease my conducted emission test. I'm going down to 73 dB microvolt per dB microvolt. So of course I did not pass the test, but just changing the technology, so one component could also influence the EMI behavior. And so in combination, when I now do some filtering, I can achieve the conducted emission test. So what I did is I built up this input filter. So this was copied from the datasheet. It's called an ultra low EMI filter setup. So this one. And I did it with our MLCCs, our ferrite bead and inductor. And then I see one thing with the aluminum capacitor, I scratched the limit. The harmonics are good, but the fundamental is I scratch. So maybe when there are tolerances, then maybe I'm above the limit. And with the polymer capacity input, I'm now with 38 dB microvolt. So now I'm safe. I also have enough space for tolerances and so on. So changing technology. So having a bad layout, but when I'm changing technology, I can achieve that I meet the specification. So I'm under the limits. But this is for EMI, and also for the output you have capacitors. So it's the same setup with from my power supply, and now I change the component here, so the output capacitor. When I just use an electrolytic one, so 47 microfarad, 16 volt ESR is quite high. I get, it more or less is the same shape what like the current goes through the inductor. So I see these the squares here. It's around 400 millivolt peak to peak. When I think about I have a 5 volt output, it's 10, more or less 10%. So this is quite high. Of course, no one would use just one capacity output. Also with this high ESR value, you have to check the stability of your regulator because this high ESR leads to also to an instability. Maybe you have to add a capacitor to the feedback. In my case, I have to do it to get a stable regulator. Where this comes from, why I get this ripple. You can also do the mathematical equation to calculate it and where it comes from. So here's now the output capacitor. You have also your ESR and your ESL. Here's the loop from the rectification and the switching. Here's the inductor, and the current goes because we have an alternating current from the inductor. There will be going through the capacitor, and due to the ESR, there will be a voltage drop. It's relating to the inductor current. So when you have a low ESR, you will get also a low output voltage ripple. So then what I did, I placed the polymer capacitor, same capacitance value and same voltage with a really low ESR. And what I see, I now get 50 millivolt as a ripple peak to peak. I also get here the spikes. This comes from the ESL. So from the low ESL, there's some resonant on my layout. So this is this is something what I can also see in the simulation when I do it with LT Spice. And then so the best thing what I can achieve is when I place then another MLCC after the polymer capacitor. When I do the parallel of capacitor, I also reduce the ESL and increase the capacitance value, and this results in a really good result of just 40 millivolt peak to peak when I go from here to here. And now I imagine I have a really good layout. So a really good layout means means for me that also some parasitics from the ESL will be removed, and then I just get 20 millivolt as a ripple, and I think this is a really good result. What we can achieve, when we are using the right the technology and combine also technologies. So this will lead to a really good performance of the regulator itself. This is also, or this is the end of my presentation for today. Thanks for listening, for joining, and now I'm here for answering your questions if they are there. Give me a few, just a few seconds or minutes to read the chat, and then I will answer the question. So one question was for lifetime calculation, where does ripple current get factored in? That is a good one because what I showed here is the basic formula. Because every manufacturer have then in advance some more specific formula. So when we have, or when we got the information from you, so ripple frequency, ripple current, and also applied voltage, temperature, we can do a more precise calculations and get a more precise lifetime calculation. So yes, in the what you see here, there is not factored in, but we do in normal. Also, is the industrial market trending toward polymer? Yes, we see this, that more and more customers are using polymer because of the higher lifetime, and because especially the industrial customers, they have to build up really reliable products, and there could be polymer really good, a good substitution about aluminum capacitors. So next one is, which one of these would you recommend for DC-Link energy storage and why? Yeah, this for me, DC-Link application or the energy storage is combined with higher voltages, and so higher voltages we cannot achieve at the moment with polymer. So we have 100-volt polymer, and the development is also going higher with the voltages, but there's a limitation, and with aluminum we can achieve 500, 650 volt. And so for this, I would recommend aluminum electrolytic, but also please keep in mind that you can use for the DC-Link application film capacitors, so special film DC-Link capacitors, which are really suitable for when you have high switching frequencies like with GaN or SiC. And then therefore I would go maybe to the film capacitors. Yeah, about the model, are capacitors well represented by a simple RLC circuit and frequency band up to 30 megahertz? Yeah, not really. There is some behavior which is not covered in a just simple RLC model, because there are some dips and some curves, or some behavior which could not modeled. What we are doing for the simple models, for example, when we are doing also implementing in LT Spice, we make a fitting, also we make a fit of the curve. But when we want to have a really precise model, we have to increase the complexity of the circuitry. So of course, for the first approximation, you can use it, but it's also good to have a more precise model. So when there's some need, please contact us and we can get into discussion. So then, do you have any recommendation for the layout for those capacitors in general? I think, so when I think about layout recommendation, I think the connection to the ground is really important, because there's, when you do some filtering, then you have a really low impedance connections to the ground. And so therefore, at least I think the rule of thumb is to place 3 wires to the pad, to the inner layer, to have a really good connection. But yeah, please check the data sheet about the pad, the land pattern. And as I said, when there's the connection to ground should be really good to have a good also low impedance connection. Then how bad is the vibration penalty for polymers, and do you have products that are vibration proof? Yeah, maybe I said that it's the vibration is not the best for the polymer, but we tested internally with 10 Gs, so it's an high vibration test, and we also test shock for the polymer, and they all passed our internal reliability, but compared to the aluminum electrolytic, they have more capability to be more vibration proof, or can handling the vibration better than the polymer. But also the polymer can easily handle the 10 G in our tests, so there's no issue with them. So this is we have also the reliability done. And then last question, on the input of a high frequency amplifier, which would be recommended for the design, electrolytic or polymer? Oof, this is hard to tell, because when it's high frequency amplifier depending on the power. Also, MLCCs have less parasitic effects than aluminum and polymer. So maybe MLCCs are good, but depending on what kind of voltages and capacitance do you need, there's a limitation maybe with the MLCCs. So we can get into discussion when you contact me directly. I can try to figure out and help, but to see to tell it here, it's quite hard. And then a question what was also upcoming, but I don't understand correctly is it seems many times that for high frequency switch mode capacitors, the series resistance is specified by the ESR directly, while for power line frequency capacitors, the tangents delta figure is given. Why is this? And is the tangents delta XA really at the same as the ESR? So honestly, I cannot answer it immediately. I will take this question with me, and when you give Amelia the contact details, I will contact you and try to figure out to try to understand better what is the also with this power line capacitors and so on in a better way. Yeah, I think that that was all questions what's coming up. One was, can you discuss the relative flammability of failure modes? So this is too much to discuss here. It would take too much time because there are certain failure modes for the electrolytic capacitors and polymer. But of course, one big difference is that the electrolytic have the vent. When there's some gas, it can go out. Polymer do not have vent because there's a solid. So there's a big difference. But about the failure modes, maybe I can do another webinar about the failure modes, or you can leave your contact details and I will contact you and maybe we can discuss it then. Yep, that was all questions. So thanks a lot for your questions. It is really nice to see that there is requests. And anytime you have other questions, please contact me, contact our colleagues. We are ready. We are happy to help. And I wish you a nice day and hope to see you soon. Bye.